Alright, physics class, hope it's going well. We got our conservation momentum, some 2D momentum. Let's go with more simple or just sort of a few questions for conservation momentum. Looking at this formula here, our MV1, M1V1, M2V2, on and on. So basically our momentum all before, momentum all after has to be equal. So I'm going to be going off of our worksheet, the first one that says constant momentum and collision practice sheet. And I'm going to go through question 1, 3, and 5 on this one for this video. So kind of just looking at some of our more simple understandings of that conservation momentum. All right, let's bring up this. Nope, this. Yes. All right, so let's see what we got here. It says a 95 kilogram fullback running at 8.2 meters per second glides midair with a 128 kilogram defensive tackle. These are, you don't really need to know the names of all these. I bring football this one because I like football and momentum. Don't really care about the names. But basically one person, 95, 8.2, collides with another person, 128, moving the opposite direction. Both players hit each other, end up with a speed of 0. How fast was the tackle originally moving? So how fast was this person originally moving? So I kind of did this in my intro video here. If I kind of look, again, momentum 1 initial, plus momentum 2 initial has to equal momentum 1 final and plus momentum 2 final. That's basically what that formula says. It just puts it into MV form. But if we have 0 momentum here because both our velocities were 0, that means these two have to cancel out. Okay? So basically here we have to have like M1 V1 plus M1 V2. These have to cancel out when it's 0 over here. Okay, so if I move it to the other side, equals negative. Like I have to have some kind of negative speed here just going the opposite direction. Okay, so let's actually kind of figure out what this is. What was the momentum of player A? Momentum of A is 95 times 2.8. So if I go 95 times 8.2, 779 kilogram meters per second. All right, now we know that this defensive tackle has to have the same momentum just going the opposite direction because it cancels out. It has to kind of end up being 0. So we'd have to know the momentum B has to also be like negative 779, okay? We don't really have directions here, so I just mean negative as in going the opposite direction. So now that I know this person's momentum, I can find the mass, okay? Mass is just momentum over velocity, okay? So if I want to get mass, I just take this. Well, one second, I need to know, my bad, I need to know velocity. Velocity equals momentum over mass. There we go. So if I have this 779 divided by 128, I know that the speed, velocity equals 6.08 meters per second. And that's how fast this player is going the opposite. And that kind of makes sense. He doesn't have to be going as fast because he's bigger, okay? The more mass that you have, the less velocity you would need to have the same momentum. So that kind of makes sense. All right, cool. A lot of these questions are going to revolve around these same 3 formulas. It's just going to be the understanding of how you get to them, okay? I'm trying to understand how you get that answer. That's why momentum can be a little tough sometimes. I like it because it's not all formula-based. I'm not a big formula-based teacher. I like the understanding of it, but it can be tough sometimes with that. Question 3. Before collision, 25 kilogram object is moving at 12 meters. So let's look at momentum A kind of initially. Okay, 25 times 12. If I go 25 times 12, I get 300 kilogram meters per second. All right. After the collision with some kind of stationary box. So we had this box, okay? So initially this box had a momentum of 0 because it's a stationary box. So this box had an actual, again, stationary momentum of 0. Okay? After the collision, so we have a now PA final, momentum of A final. I guess I should put in these P's in more lowercase, but it's hard to have a lowercase p with a little subscript. 25 and now at 8. So now we have 25 times 8, which I think is 200, but let me just do my due diligence. 25 times 8, 200 kilograms meters per second. Okay, it says, what is the resulting momentum of the box? So basically, this is just asking, how much momentum does box B have? It's not asking for velocity or any of that kind of stuff. Just how much momentum does it have? Well, if before I had 300 and 0, that was my 300 and 0, and so that's what this would work out to. Okay, your MVV one is this, 300 plus 0, so 300 beforehand. Now if I have momentum here of 200, well, the box has to have momentum B has to be equal to 100. Has to be 100 kilograms, meters per second. That's a horrible answer. Okay? And that's because, again, there's 300 beforehand, it has to be the same afterwards. If this object still has 200, the box now has to have 100. All right? It doesn't give a mass or anything, so we can't find a velocity. That's all we need right there. Cool. Let's go to question 5. Question 5. It says a 15-gram bullet. And to put that in perspective, please turn that to kilograms. 0.015 kilograms. Let's put everything in kilograms, okay, as well as meters per second. Okay, is shot into a 5.085 kilogram. All right, wooden block standing on frictionless surface. The block with the book in it acquires a velocity of 1 meter per second. Calculate the velocity beforehand. Okay, so we have kind of the masses beforehand, and we're giving a kind of like total after. Now, these two things eventually get stuck. Okay, so let's think of kind of like momentum before, okay, initial, and momentum final. We don't have kind of two objects anymore on this side. We have one, this bullet embedded itself into the block, which means we only have one object, okay? This is kind of called like an inelastic collision, where two things like hit each other and then have a total mass that's basically all together because they actually stick together. So when this happens, we find to get this, we have velocity multiplied by mass total. Okay, what's the total mass of both of them together? Our velocity is 1, and if I add these two up together, I get a mass of 5.1 kilograms. Okay, and so I know that my momentum after the collision is 5.1 kilograms meters per second. All right. So this is my after. I know that the after this, that was with momentum. This was the bullet, and it was shot into a wooden block standing still. Basically, it was standing like on its own. So this actually had a velocity of 0, which means that when we look at our M1 V1 and M2 V2, one of them was 0, which means all the velocity had to come from this. All the velocity had to come from the bullet. And so now that I know that, all I have to do is find like M1 V1, which means I know M, 0.015, has to equal this. So all I have to do is basically like divide, like take this over, divide, and divide it over here, 0.015, to get my velocity of this one. Kind of similar to what we did ish in our lab last week. We had like the final, we need to find one of those initial cart ones. Similar idea here. So if I take that 5.1 divided by 0.015, I get a velocity of 340 meters per second. So that's how fast the bullet is going beforehand, before it actually hit this block. Okay, so hopefully those first ones, again, kind of make sense. They're all using kind of the similar formula. It's just really understanding the before, the after, and what's happening there. So hopefully that makes sense. We're gonna have 2 more videos, one kind of going again with conservation of it, and then one that might be a little longer talking about the 2D aspect, the different directions and that kind of stuff. So, all right, class, thanks so much. I'll talk to you later.